Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll discuss the third and final method for solving complicated integrals, which is referred to as integration by parts. And this is sort of like the inverse of the product rule in differentiation. So we'll start with that. We know the product rule in differentiation, which tells us d by dx of u into v is u times dv by dx plus v times du by dx. From that I can write u dv by dx is equal to d by dx of uv minus v du by dx. Now if we multiply both sides by dx and then integrate, what we'll get is integral of u dv by dx times dx is equal to integral of this into dx. Now this is the derivative of uv, the integral of that will be uv, right? Because this dx will cancel with that dx, the integral of d of uv will just give me uv. So this will be equal to uv minus integral of v du by dx into dx, right? So this is essentially the formula of integration by parts. Whenever you have an integration of the form of the LHS, in which you have one function multiplied by what looks like the derivative of some standard function. Remember, all we are looking for is standard functions, because from that we can make complicated integrals. So if we see the form of a function such as it is the product of two functions u and the derivative of a standard function v, then we can generally use this formula, where if we know u and v, this term is clearly known. And often if u and v are standard functions, this integral might be easier to solve than this integral. That's the only case in which integration by parts is useful. This equation is always valid, but this is only helpful if this integral is easier to solve for us than this integral. This is not really an integral, this is just a value, right? So that does happen in many cases. We'll see some examples, but before that I'll just write down this statement in words, because that's generally the way students remember it. This basically, you can remember this as, you can call one of these the first function and the other the second function, right? In this case we'll call u the first function and dv by dx the second function, and we basically have to calculate the integral of their product. So just an example could be integral of x cos x dx, right? In this case you could take x to be the first function and cos x to be the second function and use this equation, or you could take x to be the second function and cos x could be the first function and then you use this equation. Whichever one gives you a simplified integral on the right, and hence the final answer will be the one you use, even though both will be correct. So basically you'll see the integral of the product of two functions, call one of them the first function, the other one the second function. Here we have u and dv by dx, and so the RHS, which is the formula for integration by parts, can be written as the first function multiplied by the integral of the second function. This is the first term, minus, so this is the first term, right? The first function u multiplied by v. V is the integral of dv by dx, right? So the first function multiplied by the integral of the second function minus, and now we have another term which is the integral of the derivative of first function into the integral of the second function. If you can remember it by this equation, that's well and good. Otherwise, this is generally an easier way to remember because you can remember the words quite easily and you remember it quite quickly. The first function multiplied by the integral of the second function. So let's say you have this. You take this to be the first function, this to be the second function. This integral of their product will be the first function multiplied by the integral of the second function, this term, minus the integral of, here you could put a bracket, the derivative of the first function du by dx multiplied by the integral of the second function, which is v. Right. So this is the formula. This is how you can remember it. Let's see a few applications. So first we'll start with the example we talked about, integral of x cos x dx. Now which one do we take the first and which one to be the second? Well, there's no, you could try both of them and ultimately one will give you the answer, one will not. But there are some rules which help us in deciding so that we don't have to do it by hit and trial. One of the standard rules is, if any one of the two products is either a power of x or a polynomial in x, in that case we take that to be the first function. So in this case, we'll take x to be the first function and we'll take cos x to be the second function. So this term will be, now we'll use integration by parts, the first function multiplied by the integral of the second function. That was the first term, right? If you could write this as u and this as dv by dx if you wanted to remind, to form an analogy with the previous case, which would give me cos x is dv by dx, so v would be the integral of cos x, which is sin x, and u is x, right? So the first term u into v, or another way you can remember it is the first function multiplied by the integral of the second function. That will be x into sin x, because the integral of cos x is sin x, minus the integral of the derivative of the first function, the derivative of x, du by dx, which is 1, multiplied by the integral of the second function, which is sin x dx. Now you see, we started off with x multiplied by a standard trigonometric function. Now we have 1 multiplied by a standard trigonometric function. We do know how to calculate this value, the integral of sin x. We find a term whose derivative, an expression whose derivative is sin x. So that is minus cos x. So this comes out to be x sin x, and then the integral of sin x is minus cos x, and you'll have another minus here. So plus cos x plus c. Now you can try to differentiate this term. The derivative of x sin x plus cos x plus c will be x cos x, and then you will have plus sin x, and here you will have minus sin x, and the derivative of c is 0. So you do indeed get x cos x. So the integral of x cos x dx is x sin x plus cos x plus c. Now there are a couple of things I want to pay attention to. The first is, we did not take any constant of integration here. When we talked about the first function multiplied by the integral of the second function, v, the integral of the second function, could be sin x or it could be sin x plus c, right, a constant. Let's say sin x plus 2. In that case, we would have sin x plus 2 here, and we would also have sin x plus 2 here, right? And the integral of 1, it's actually better if I just show it to you. So what would happen if instead of sin x we take it to be sin x plus 2? The first term would be x times sin x plus 2, then minus integral of 1 into sin x plus 2, so we just remove this 1, dx. Right, now this is sin x plus 2, not sin of x plus 2. So this is x sin x plus 2x, and then the integral of sin x is minus cos x, so plus cos x. Then you have minus integral of 2 dx, that is minus 2x plus c. So 2x and 2x cancel. We once again get the same answer, x sin x plus cos x plus c. So we see that in this first term, u into v, the first function multiplied by the integral of the second function, in that we don't really need to include the constant of integration because it ultimately cancels out anyway. Now let's see what would have happened if instead of taking x to be the first function and cos x to be the second function, we would have reversed it and taken cos x to be the first function and x to be the second function. So in that case, we have integral x cos x dx. Now we take cos x to be the first function and we take x to be the second function, and the result we'll get is the first function cos x multiplied by the integral of the second function, which is x squared by 2. So we'll get cos x times x squared by 2 minus the integral of the derivative of the first function. The derivative of cos x is minus sin x. So we can write a plus here, and sin x multiplied by the integral of the first function, which is x squared by 2 dx. So you see, now it's gotten harder. We started with x cos x, which is x multiplied by a standard trigonometric function. We end up with x squared multiplied by a standard trigonometric function. So this is not the right way to go. In fact, if we would have had x squared sin x, the integral of that, we would have applied integration by parts, got this first, and used another integration by parts to get the value of this. So you see, even though this identity is true, the LHS is indeed equal to the RHS, it's of no use to us because we cannot calculate this integral. So what we do is, we take x to be the first function and cos x to be the second function, which allows us to evaluate the value of this integral. Let's look at a few more examples. We left out one example when we were doing the standard integrals, that was ln x, right? We saw that the integral of 1 by x is ln mod x, but we didn't see what the integral of ln x was. So let's see what that is. Ln x dx. And you can actually calculate this using integration by parts. What you do is, you write it as 1 into ln x. This is the trick which you use. So you take 1 to be one of the function and ln x to be the other function. So in this case, what we'll do is, we'll take ln x to be the first function to be the second function. So we have this will be the first function ln x multiplied by the integral of the second function. The integral of 1 would be x. So x ln x minus the integral of the derivative of the first function. The derivative of ln x is 1 by x into the integral of the second function, which is x dx. So we have x and x cancelling. The integral of 1 dx is x. We'll have another plus c. So this is x ln x minus x plus c. By the way, technically if we wrote plus c for this integral, this would be minus c, but I don't take care of that, and I hope you understand why. I just put a 1 plus c at the end unless something unusual is happening, and as long as everything is linear, because every constant can be replaced by another constant. So the net function plus some arbitrary constant. So this is a result which now you should remember. And if you have a list of the standard integrals of the standard functions, you can add this to the list. The integral of ln x, which you will use quite frequently, is x ln x minus x plus c. If you want to check it, you can differentiate this. That will give you ln x minus x into the derivative of ln x, which is 1 by x. Sorry, plus x into the derivative of ln x, which is 1 by x, minus the derivative of x, which is 1. These two cancel, and this gives me ln x. So indeed, the derivative of the RHS is ln x, which means RHS is the integral of ln x. Let's look at one more example, and in this example, we can actually calculate it by both ways. The rule I gave you was that if there's a polynomial in one of the two, you take that to be the first function. But if we calculate something like integral of e to the power x sin x dx, a product of two standard functions, one trigonometric and one exponential, we can take any of these to be the first or the second function, and I'll try to do it in both ways and show you that the answer is the same. So first, let's take e to the power x to be the first function and sin x to be the second function. In that case, this would give me the first function e to the power x multiplied by the integral of the second function, that is the integral of sin x, that is minus cos x, minus the integral of the derivative of the first function, which is again e to the power x, into the integral of the second function, the integral of sin x, which is minus cos x. So the minus and minus give me plus cos x dx. Now actually we haven't solved it, but we've taken one step further, because we've converted the e to the power x sin x integral into an e to the power x cos x integral. Now what's going to happen if we calculate the e to the power x cos x integral? Let's try to calculate that. And we'll do the same thing. We'll take e to the power x to be the first function. So this will be the first function e to the power x multiplied by the integral of the second function, the integral of cos x, which will be sin x, minus the integral of the derivative of the first function e to the power x into the integral of the second function, which is sin x dx. Right. So now we converted e to the power x cos x back into e to the power x sin x. We can substitute this upstairs, and what we'll get is this equal to, which gives us here, which is the integral for this value, is minus e to the power x cos x plus e to the power x sin x minus, and now I'll just call this I. Let's say the integral of e to the power x sin x dx is I. So this is I, but the LHS is also I. Write this. Now from this we can get 2I is equal to e to the power x times sin x minus cos x, which gives me I is equal to e to the power x sin x minus cos x divided by 2. And obviously you can add a plus c. So this is the answer. So in this case you did not get this integral explicitly, you got this to be equal to an implicit expression in which this was involved. You took the RHS, the I in the RHS to the LHS, and you were able to calculate this value. Let's try to do the same thing by taking sin x to be the first function. So now sin x is the first function. And e to the power x is the second function. So this will come out to be the first function sin x multiplied by the integral of the second function, which is just e to the power x, minus the integral of the derivative of the first function, the derivative of sin x, which is cos x, multiplied by the integral of the second function, e to the power x. Once again we see a similar thing. To calculate this, we'll take e to the power x cos x dx, and we'll do the same thing now. We'll take cos x to be the first function. So this is cos x, the first function, multiplied by the integral of the second function, minus the integral of the derivative of the first function, the derivative of cos x, which is minus sin x, so plus sin x, and the integral of the second function, e to the power x dx. Putting this here, what we get is this, which is I is equal to e to the power x sin x minus e to the power x cos x minus I once again, which means 2I is equal to e to the power x into sin x minus cos x, which gives me once again the same value, e to the power x into sin x minus cos x by 2 plus c. So basically when you see two standard functions or standard expressions and they are in the product, the integration by parts method should be a first line of defense. When you just try to solve it by using one of them as the first function, then the other is the first function. If that doesn't work, then you go back to one of the previous methods, either partial fractions or try to do it by substitution. Finally, let's just take one standard type of integral which can easily be simplified by integration by parts. This would be any function of the form of, any integral of the form of e to the power x times f of x plus f dash of x dx. Right, so e to the power x times a function plus its derivative. So this could be, for example, e to the power x times sin x and then plus the derivative of sin x, which is cos x. It could be e to the power x times tan x plus the derivative of tan x, which would be sec square x. It could be e to the power x times the sum of two polynomials where one is the derivative of the other. So it's mainly a trick of spotting an expression and trying to reduce it to this form. Once you reduce it to this form, you can easily use integration by parts. So this comes out to be integral e to the power x f of x dx plus integral e to the power x f dash of x dx. Now in this second term, I'll use integration by parts. And what I'll get is, this will just stay the same, integral of e to the power x f of x dx plus, so the first function multiplied by the integral of the second function, so e to the power x times f of x minus the integral of the derivative of the first function e to the power x into the integral of the second function f of x dx. Now this cancels with this, there's obviously a plus c here, and it comes out to be e to the power x f of x plus c. So this comes out to be this. The integral of e to the power x times fx plus f dash x is e to the power x fx plus c. And from this you can actually see more clearly why. If you differentiate this, first you'll get e to the power x times fx, the first term of the product rule, this into the derivative of this, plus e to the power x times the derivative of the RHS, which is f dash of x. So just as a quick note, the integral of e to the power x times tan x plus sec square x will be e to the power x tan x plus c, and if you differentiate this, you'll get e to the power x times tan x plus sec square x. This completes integration by parts, and up till now we've only seen one type of integration, which we call indefinite integration. And that's the type of integration in which you have this constant of integration appearing. There's another form of integration which is just a sort of add-on to it. Most of the information about integration you already know. That's called definite integration, and that will be the subject for the next video. Thank you.